Hello viewers, welcome back to the course on matrix computation and its application. So, in the previous lecture we have discussed the process of the Gram-Smith, that how we are able to convert the given set of linearly independent vectors into the orthonormal vectors. So, today we will discuss the application of that one. So, let us take the example that how we can proceed with the Gram-Smith process. Suppose I have a vector space R3 and I have the basis, I am taking the basis as 1 1 1 0 1 1 and 0 0 1. So, this is the basis I am taking. Basis of R3. Now, from there the process is that the question is that convert it into orthonormal basis using Gram-Smith process. So, now, I call it, maybe I will call it V1, V2, V3. So, these are three vectors I am taking. So, let us take U1. So, it is V1 divided by its magnitude. So, it is V1. So, from here V1 is 1 1 0 and its magnitude is 1 plus 1 under the root. So, it will become 1 by root 2 1 1 0. So, that is my vector U1, is a normalized vector. So, it is step 1. Now, step 2, I want to make another vector. So, I will write my Y2. So, it is my V2 minus taking the dot product of V2 with U1 into U1. So, my V2 is a vector, that is a column vector, we always represent by this one, minus. So, I am taking the dot product of V2 with U1. So, V2 is basically, I can write here like V2 is 0 1 1, taking the dot product with 1 1 0 root 2. So, this is my dot product, and then U1 is, I can call it maybe 1 by root 2 1 by root 2 0. So, how I am going to solve this one is that this vector minus, so I am taking the dot product of this. So, 1 by root 2 I can take common, no problem. So, from here it is 1 0. So, 0 1 1 and 0. So, if you see from here, this will become 1 by root 2 and then 1 by root 2 1 by root 2 0. From here I can write this will become equal to 0 1 1 minus. So, 1 by root 2 I can take inside. So, it will be 1 by 2 1 by 2 0, and I am subtracting this vector and this vector. So, component wise I will subtract. So, it becomes minus 1 by 2, 1 minus half, it will be 1 by 2, and 1 minus 0, it will be 1. So, I am getting this vector. So, that is my Y2. So, I am getting this value. Now, from here I will write my U2. So, I will take this vector as minus half half 1, because this is how we can find from here, divided by its magnitude. So, it will be 1 by 4 plus 1 by 4 plus 1 root. So, it is 1 plus 1 2 plus 4 6 by 4. So, it is, I can write as minus 1 by 2 1 divided by, so it is 6 by 4. So, 3 by 2 root 2. So, that is my u2. So, this is a normalized vector. Now, from here so I am able to get my u1 is basically, this is the vector 1 by root 2 1 by root 2 0, and I am able to get u2. So, u2 is this one root. So, I can write from here, now I can write minus 1 by 2 into root 3 and root 2. Now, from here if I multiply by this one, I can write as minus root 2 by 2 into root 3. I will multiply by root 2 and root 2. So, this will cancel with this one, and it will become minus 1 by root 6. So, this one I can write as root 6. So, I can write from here minus 1 by root 6, then 1 by root 6, and in the end it is 1. So, it is just I am writing here root 2 by 3. So, from here I can write 2 by root 3, because it is 1 by, and this one I can write so I multiply by root 2 and root 2. So, root 2 into root 2 2. So, I can write this as this one. So, I can write from here this one. This is my u2. Now, I will write my next vector y3. So, this will be v3 minus, I am taking the component of v3 with u1 into u1 plus v3 taking the component with u2, and that will be equal to, so v3 I have taken 0 0 1. So, it is 0 0 1, and I know that these vectors are linearly independent. Now, from here I get 0 0 1 minus, now I am taking the dot product of v3 with u1. So, it is 0 0 1. So, it will be, I am taking with u1 the v3. So, v3 is, so it will be v3, so it will be 0 plus v3 with v2. So, it is v3 with dot taking the dot product. So, it will be 2 by root 6 into my u2. So, that u2 is, so I am taking the dot product. So, it is just 2 by root 6, and then it is again the whole vector, that is minus 1 by root 6, 1 by root 6 and 2 by root 6. This is what I got. From here I can write is as 0 0 1 minus, now I can multiply by this. So, I can just take inside. So, it will be 2 into 6. So, it will be minus, because it will be minus 2 by 6. So, it will be minus 1 by 3. Now, it will be 2 by 6. So, it will be 1 by 3, and it is 2 into 2 4 by 6. So, that will be 4 by 6. So, it is 2 by 3, this one, and from here I get this value. This vector will be, so this minus this, so it will be 1 by 3, this minus this, it is minus 1 by 3, and 1 minus 2 by 3 is 1 by 3. So, that is my y3. So, this is my y3. Now, from here I can find my u3. So, u3 I am just taking this vector 1 by 3 minus 1 by 3, 1 by 3, and divided by its magnitude. So, its magnitude will be 1 by 9 plus 1 by 9 plus 1 by 9 under the root. So, 3 by 9 under the root, and this is 1 by 3 root 3. So, it is 1 by root 3. Now, from here I can write, see, 1 by 3 divided by 1 by root 3. So, I am getting my root 3 above, and from here I can write this as 3 So, from here it becomes 1 by root 3, because I just multiply by root 3 and divide by root 3. So, this can be written as this one, and from here is 3. So, that will cancel out this. So, from here I can get this vector as 1 by root 3 minus 1 by root 3 and 1 by root 3. So, this is my vector u3. So, from here my u3 become minus 1 by root 3 and 1 by root 3. So, let us check that. Now, we are able to get 3 vectors. So, this is my u1, u2 and u3. Now, I want to check that whether they are linearly they are orthogonal to each other or not. Now, from here we can see that if I take u1, it is no problem. Now, if I take u1 dot u2, so this is 1 by root 2 minus 1 by root 6 plus 1 by root 2 minus 1 by root 6, and last is, so it is cancel out. So, that is 0. Now, u1 dot u3. So, u1 dot u3, it becomes 1 by root 2 into 1 by root 3 minus 1 by root 2 into 1 by root 3, because it is a negative sign and third is 0. So, this is also cancel out, become 0. Now, I take u2 u3. So, u2 u3 is minus 1 by, so I am taking 6 into 3 18 minus 1 by 18, because this is negative sign, plus 2 by 18, and that will be 0. So, they are orthonormal to each other, and of course, their magnitude is 1, because it is 2 4 plus 1 plus 5 plus 5 plus 6. So, if I take this one, its magnitude is 1, its magnitude is 1 and its magnitude is 1. So, from here we can say that now the set, I call it this one. So, I represent by 1 by root 2, 1 by root 2 0, and then minus 1 by root 6 2 by root 6, and the third one is 1 by root 3 minus 1 by root 3 and 1 by root 3. So, this is an orthonormal basis of R3. So, we have changed the basis from B, that is the linearly independent basis, to the orthonormal basis. That is the another basis of R3. So, you can also that this is change of basis. Now, after doing this one, what we are going to do is I am going to use this basis in another form, and that we are going to discuss is, now what I am going to write is, from here if you see, then so after doing this one, I will just write the matrix. I represent this matrix by Q. So, in the Q, what I am writing? I am writing this column, this vector as column vector minus 1 by root 6 1 by root 3 minus 1 by root 3 and 1 by root 3. And I know from here that these are orthogonal to each other. This is 3. Now, because the columns are orthogonal to each other, even I represent by this is my R1, R2, R3. So, I can take my dot product with R1, R2. So, it will be 1 by 2 minus 1 by 6 minus 1 by 3. So, this is, it can be written as, so I can take the LCM over here. So, it is 6. So, it is 3 minus 1 minus 2. So, 3 minus 3 by 6. So, it is 0. So, R1 is orthonormal, R1 dot R3 we can take. So, this is again minus 2 and minus 2. So, that will be also 0, and R2 dot R3, that is also orthogonal to each other, because here it can be 2 by 6 minus 1 by 3. So, it is 0. So, from here I can say that my Q is an orthogonal matrix. Now, what we are going to do is that, now we have the basis. So, for the R3 we have two bases, B, that is my V1, V2, V3, and we have another basis S, that is my U1, U2, U3. Now, I know that this is the orthogonal basis. So, I can write my V1 as linear combination of the standard, this orthogonal basis U1, U2, U3. How I can write? I can write V1 as V1 dot U1, U1 plus V1 dot U2, U2 plus V1 dot U3, U3. Similarly, I can write my vector V2 as V2 dot U1, U1, V2 dot U2, U2 and V3 dot V2 dot U3, U3, that we have already discussed. And similarly, V3 is V3 taking the dot product with U1, V3 taking the dot product with U2, and V3 taking the dot product with U3. This system, this can be written as, so I take a matrix with first column, second and third. So this is the matrix basically we have, which is made up of the bases, the linearly independent bases. I can call it this matrix A. So this can be written as, now I can write this as U1, U2, U3. So that is, I am taking U1, U2, U3 here. So we call it Q, and then I can have a matrix here. This can be written as V1 dot U1, then V1 dot U2 and V1 dot U3, because this one, because I multiply by this one, I will get this value. Now V2 dot U1, V2 dot U2 and V2 dot U3. Similarly, I can have V3 taking the dot product with U1, V3 taking the dot product with U2 and V3 taking the dot product with U3. Now from here I know that this V1 is U1, so no problem. But what about V1 dot U2? I know that V1 is perpendicular to U2. So from here, if you see, so this is another matrix, but from here you can see that this value is equal to 0, because my U2 is definitely perpendicular to U1 and U1 in the direction of V1, so it is perpendicular. Similarly, my V3 and U3, V1, U3 are 0, so this is also 0. Now in the next one, V2 dot U1, V2 dot U2 and V2 dot U3, that is 0, so this is equal to 0. Now this is okay. V3 dot U3, because now V2 dot U1 and V2 dot U2 and V3 dot U1, V3 dot U2 and V3 dot V3. So if you see from here, all this value will be there, but this value will be 0. So and it is a 3 cross 3 matrix. So I can call this matrix R, and this is, I can know from here, this is upper triangular matrix. Because here it is V2 with U1, no problem, V2 with U2, no problem. So this is, it can be some values, but this value definitely it will be 0. So this is a matrix that is called the upper triangular matrix. So from here, if you see, I have written my matrix A as Q, this is made up of orthonormal bases into R. So this is called QR factorization of matrix A. Now from based on this one, we will take the idea of another important topic, that is QR factorization. Or we also call it QR decomposition. So, what is this? So, we have a vector space V be a vector space, and I call it the dimension of V is suppose n. So, now I take the basis of V. So, let B is the basis, that is V1, V2, Vn. So, this is the basis. Then we take the orthogonal basis, that is U1, U2, Un. So, this is what we have seen. So, this is a basis of V, and this is a orthonormal basis of V. So, these are the orthonormal bases that we have taken from with the help of Gram-Schmidt. Now, based on this one, we can write again. So, now we can write V1 as, again we can write V1 taking the dot product with U1, U1, V1 taking the dot product with U2, U2, and in the end V1 with Un taking the dot product with Un. In the end we can have my Vn as Vn dot U1, Vn dot U2 and Vn dot Un. So, from here I can write a matrix with V1 column vector, V2, Vn. It can be written as U1, U2, Un, and then we can have a matrix that is I can write as V1 dot U1, this is a dot product we are taking, V1 dot U2, V1 dot Un. So, this is a dot product we are taking, we understood. Now, from here I can write again. So, this is V1. So, I can write the same thing with V2, V2 dot Un, and in the end we will get Vn dot U1, Vn dot U2 and Vn dot Un dot product. Now, this matrix is my matrix corresponding to the given basis. I call it A. This is a matrix corresponding to the orthogonal basis, that is my Q, and this matrix, if you see now from here in this matrix. So, this matrix I can write here that from here it is for now Vi dot Uj. So, this is equal to 0 for j is greater than equal to 2, okay, and where I is 1, 2 up to j minus 1. So, that is there. So, if you use this one, then you will see that this matrix is an upper triangular matrix, because here we are talking about the vector space of dimension n. So, this matrix will be of order n cross n, this will be also of order n cross n, and this will be also of order n cross n, because we know that when the matrix is a square matrix, only then we can talk about upper triangular matrix. So, from here we get my matrix A is equal to QR. Now, my Q is an orthogonal matrix Now I can find the R, because here I know the value of A, I know the value of Q. So, I should be able to get the value of R directly from there. Now, it is a orthogonal matrix. So, I can take the inverse. So, Q inverse A I can write as R. Now, I know that the Q inverse is equal to transpose, because it is a orthogonal matrix, and from here I can write that the Q transpose A, it can be written as equal to R. So, now with the help of Q and A we are able to find the R. So, this is my upper triangular matrix, and from here this is called, the process is called the QR factorization. So, it means I am able to factorize my given matrix A into product of two matrices, that is Q and R, and Q is the orthogonal matrix corresponding to the orthonormal basis, and R is my upper triangular matrix. So, this is all we can discuss about the QR factorization, and we can also verify this one with the, for the given matrix, the Q and R. So, that things we will discuss in the next lecture. So, in this lecture we have discussed the another important concept, that is the QR factorization, that in the, for a given matrix we can convert this matrix into the, or we can factorize this matrix in the form of Q and R. And in the next lecture we will discuss some MATLAB commands or Octave commands, that how we can verify these things very easily in the software like MATLAB or Octave. So, thanks for watching, thanks very much.